Alright, hi y'all. Today we're going to be going over this type of diode problem. Now, this isn't, well, I guess this is just your typical diode problem where you're trying to figure out what is V out in terms of V in, or, your resistor parameters. And you also need to figure out, especially for diodes, you need to figure out at what V in values does our V out change. So that's something you need to take, consideration of. So before we start, we have to notice what is our relationship? What is V out? Well, V out is the voltage drop across D2, the voltage drop across D3, and the voltage drop across R. Okay, so we are going to assume our voltage drops across the diodes are 0.7 volts. Okay, and we have no, have no RD value is 0, so whenever you make your diode kind of characteristics, we're going to let RD be 0. Okay, and now R, I only have R values because we don't really need to, we're not solving for actual values, we're solving for an equation. Okay, so something we have to notice here is we have two diodes in series. Let's think about this. A lot of this is having an idea about how diodes work. And how diodes work is if we make our IV characteristic of diodes, IV, your characteristic of diodes, what we notice is we have this sort of, this is for ideal diodes, by the way, so I'm not making any kind of other graphs. This point here, when voltage reaches this point, the diode will start conducting. What I mean by conducting is it'll start passing current. And this point is our VDO, our voltage drop. Okay? So that means each diode, for this diode to start conducting, it needs to be at least 0.7. It needs to be at least 0.7 volts. Now, what that means for us, though, I'm going to try and take this as easily as possible and as understanding as possible, because these are, our first introduction to semiconductors. What we have to do is we have to assume that D2 and D3 are first conducting. So if we assume, so this is for case 1, let's say D1, D2, and D3 are conducting. So they all have a voltage drop of 0.7 across them. So what we can do is we can redraw our circuit. There's going to be a lot of redrawing, by the way. All I'm going to do is plus minus 0.7 volts. And this is my D1, by the way. Also, this does not mean it's an open circuit. All I'm saying, you know what, I'm not going to put this open circuit because that looks confusing. What we have here is a voltage drop. I'll use like an EMF model or a battery model. We'll say this is V in, and we have here 3R. Okay, that doesn't change. And now we have these other diodes here. And we are having this model. Okay, and you might be wondering, why do I put this kind of battery in this way? Well, if we remember from, I guess you used it in physics for EMF, they always had this longer leg here as positive, and we want these diodes to have a voltage drop. So you go from plus to minus, you have a voltage drop of 0.7 volts. And this corresponds to this configuration of the diode, where we have the arrow is the direction of current, and that's the direction of voltage drop. So we have like this weird arrow. If you would put like a line here, this here is going into the diode. That should be the way you draw it. And of course, we know our V out is over here. So what would V out be? If we know this is a voltage drop model, right? We have 0.7, 0.7, so we know V out has to be at least 0.7 plus 0.7. And now we have to add the voltage drop across R. So I'm going to put VDR, right? This is the voltage drop across R. But what is the voltage drop across R? Well, this might be a little confusing for most, because this is definitely hard to see. I think there are two ways to do this. One way is to take this big loop here. Actually, no, there's only one way here. You take this big loop and you try and find out what R is compared to Vn. And if you notice, this is a voltage divider, right? We have 3R up here and we have R right here. So how much voltage is being supplied to that resistor? Well, if we take a voltage divider, we have the voltage across R is equal to the voltage being supplied to R times, or, I'm not going to put V in because it's technically not V in. It's going to be, we'll call it, actually, no, let's just call it V in, whatever. It's going to be this times R divided by R plus 3R. Now, I would kind of stumbled on my words saying it's not V in because it's technically not V in. We have to worry about these voltage drops here. How do we take care of that? Well, remember, the voltage that's being applied to the R value is not V in, it's V in minus 1.4, or 0.7 plus 0.7. Okay, so now VDR is equal to Vn minus 1.4 times, this simplifies to R over 4R, or 1/4. So what we have is 1/4 times Vn minus 1.4. And this is our VDR, our voltage across the resistor. So V out will be equal to 1.4 plus 1/4 times Vn minus 1.4. But for what Vn? Because Vn is very important here. Well, what's going to happen to Vn if, let's say at an extreme, let's say Vn is 1.4. So this is, by the way, this is just kind of examples. These aren't, I'm not trying to give you an answer here. I'm going to give you an answer in just a second, but I'm giving you examples here to work out in your head and try and think about this. So if we let Vn equal 1.4, well, then V out, according to our equation, we plug in 1.4 here, we see this entire thing is 0, so V out is equal to 1.4. Now, does that make sense? Well, sure it does. What this is saying then is V in here is 1.4, so the voltage, remember, this has to be at least, this is always 1.4 if it's greater than 1.4, because there has to be a voltage drop of 0.7 and 0.7. This is not a resistive, this is not a variable voltage drop. This is set by the diode itself. This does not change in ideal, in the way we're solving this. In ideal scenarios, this does not change. So this will be 0.7. So V in must be at least 1.4 for these diodes to be conducting. And for this equation, V out will stay the same. So this means this equation is true when V in is greater than or equal to 1.4 volts. So this is how you get your first part of the equation. Now, what if Vn is less than 1.4? So let's say now Vn is less than 1.4 volts. Okay. So now you might notice, this means this voltage, the diodes don't have enough voltage supplied to them to turn both of them on. Only one diode will be turned on. So if only one diode is turned on, we have, I'm going to try and make this quick because trying to make this quick because I don't want to take too much of your time. What you notice is, and by the way, because these have different branches, the voltage across them will stay the same. Remember that. That means D1 will always be on because it has, it's close. It's going to be this loop here. It's just going to be this. So Vn will always be on as long as it's greater than 0.7. So as long as Vn is greater than 0.7, then this D1 here will always be on. So we have plus minus 0.7 volts. So there will always be current flowing through this resistor R here. Okay, and now we have what, 3R here. And remember, this is when Vn is less than 1.4. So now what we have is we have one of the diodes on, plus minus 0.7, but the other one is an open circuit, so we have 0 volts across it. Well, that isn't good because that means this R here becomes shorted because there's no current going through it. We need no voltage across it. So this is a short circuit. What about this one? This is the same thing. There's no current going through that. So that means this is shorted here. So that means V out. What is V out? Well, V out, if we take this loop here, must be V in. Now, you might be asking, well, why don't you do this loop here? And it's 0.7 always, right? Because if you're between 0.7 and 1.4, this diode will be turned on. Well, that isn't the case. Now, I'll show y'all. I'm actually going to do some, video of this circuit built out and show y'all, that isn't true. Because in practicality, this voltage here, this diode is still conducting a very, very tiny bit. And it's actually going to be the same voltage across this. And in actuality, because this is shorted, because the 3R and this R are shorted, that means the voltage across both of these will be V in. In ideal cases, it isn't, though. I'm not sure why, but that is just the case. I guess really it's because the diode, yes, it can conduct, but V in and V out, KVL must be true. So in actuality, if I want to redraw this into the actual value here, this will actually be this. Plus minus V in over 2, plus minus V in over 2. So you'll have V in over 2 on both of them because KVL must be true. So this loop must be V in. And it's because they're shorted, those resistors are shorted, and those diodes must have that value of V in. Those diodes, must add up to be V in because they're in parallel with V out. Okay, so anyways, this would be the equation for V in is less than 1.4. But what about less than 0.7? That means, this here isn't going to be, this diode 1 won't be conducting at all. So this was 0.7 less than V in, or less than V in, less than 1.4. But what about when V in is less than 0.7? Because now we take it to be that V in value. This D1 won't even be conducting at all. And if you've seen what's happened with this and understand it, you'll know exactly what D1 will be. D1 will be Vin, because R will be, this entire branch will be open circuited, so there's no current going through R, meaning it's shorted. Then the voltage across that diode must be Vin. Okay, so we can draw this out here. This will be open circuited. This will be R, and this will be actually shorted. This will be plus minus Vin. 3R again is shorted because we don't have enough voltage to supply these diodes to be on. So we open circuit. I'm not even going to bother drawing that resistor. Again, it's shorted. And what do we have here? Well, we have this has to be Vn plus minus. This has to be Vn, what, over 2? Because this is also Vn over 2. So what do we notice? Well, plus minus V out. V out is Vn again. Wow, okay. So V out is equal to Vn in this case, and V out is equal to Vn in this case. This means for anything less than, what, 1.4, we have V out is equal to Vn. So according, to our analysis here, we have V out for Vn is less than 1.4. It has to be less than. If it becomes equal to, it will start, both the diodes next to V out will start conducting. So then what we have is V out is equal to Vn. But what about the other one? We already said V out is equal to 1.4 plus 1/4 Vn minus 1.4 when Vn is greater than or equal to 1.4 volts. So that'll be our answer here. You may be asking, what if it's way greater than 1.4, 100 volts, It's going to be the exact same thing. R now is going to be the exact same equation. R will just have, higher voltage across it. Be very careful when you use those high voltages. Make sure your resistors are within boundaries, your watts, your power rating of the resistors. Make sure that's careful. But that's our answer here. So hopefully, I'm probably going to start showing y'all the actual breadboard that I built here, and very simple, just showing y'all that this is true. So hopefully y'all like this kind of setup. Okay, so what we're going to be doing is we're going to be simulating this kind of, ideal case versus our practical case here. And yeah, so that's pretty much what we're going to be doing. We have our diode facing down. So if you can see this little, let me zoom in real quick here, right there. Yeah, so you see the little lines are going to be pointing, down in the diode direction. We also have the same thing over here and a little up here, right there. And we also have each resistor is going to be a 1K resistor. And these are your typical diodes we use in class in the lab. I believe 4006. Let me check. I believe they are, yeah. Yeah, 1 in 4006. So they have a 0.7 voltage drop across them. Now, that's only when they reach 0.01 amps or 10 milliamps. Here, I'm not working with 10 milliamps. I believe I'm working depending on what the voltage is here. If you guys can see that here. Right now, I have it set to 1.1. You can increase it to, let me turn this off real quick. You can increase this to like, I guess if we wanted to, we could go to like 6 volts. That way, maybe we could get closer to our 0.7 milliamp or 0.1, or I say 10 milliamp kind of range. So I'm going to set this to be 5 volts, and maybe there will be some output of 0.7 across the diodes. Now we'll check that here with the multimeter. And just to make sure here, actually, I'll read the value for the voltage. So we have 5 volts across. And now we have about 0.6 voltage drop. Okay, so what you'll see in a practice problem, if you're given something like this, is your VDO instead of 0.7 will be 0.6. Now, we noticed while we were doing our analysis on paper, we noticed Vin has to be, what, greater than or equal to 1.4. That's twice the voltage drop across the diode. So our Vin will have to be at least 1.2 for this circuit here at 5 volts input. So what we'll be using is, that 1.4 plus 1/4 Vn minus 1.4 equation. Now that equation will change a little bit because our Vn is not 1.4 anymore. So anytime you see a 1.4, replace it with, what did I say here? 0.6, right? We saw 0.6. So replace it with about 1.2. So what we'll have is 1.2 plus 1/4 Vn minus 1.2. Okay, so what will our Vout be then if we have it at 5? Well, we have, use my calculator here if I can find it. Where'd it go? Oh, there it is. So what we'll do is we'll have 1.2 plus, nice, plus 1/4. What is our Vn? Well, our Vn is 5 minus 1.2. So our Vout should be about 2.15 volts. So we'll check that. So our Vout is the voltage across this diode down to here. So what we'll do then is we'll test this with this. Oh, well, no, it's on. There we go, yeah. So about 2.13, and we have some loss. So that works. So that equation will work. And you know what we'll do is we'll change it closer to the bounds. Remember, Vn has to be at least 1.2. So what we'll do is, oh my gosh, nice. Our Vn will change Vn to be, if y'all can see that, we'll change it to be about 1.5. Oops, don't want to see 50 volts. Sorry if that's loud. I should I should see the instructions to change the sound because that's kind of annoying. Anyways, here, let me see. All right, let me get that right. Okay, so about, we say 1.5 volts. So it should still go off of this equation because it's still above 1.2. So let's change 1.5 to 1.5. Oh my gosh. So we'll see about 1.275, so about 1.3 volts across. So it's already outputting. Okay, so we'll test. Okay, so we see about 1.11. Okay, that's pretty close to our theoretical value. Let me check it again. 1.2 plus 0.25 times, what is that? 1.5 minus 1.2. Yeah, about 1.275. It's pretty close. So our theoretical matches within reason to our practical equation. But now, what if we change it to be 1.2? So let me change this. 1.2, remember, 1.2 should still follow our equation. Okay, so 1.2 is being outputted now. So if it's 1.2, it should just be what? 1.2 output, right? Or about, okay, 1 volt. Okay. So it's close. Of course, you're going to have some error here. But that is how it would work. And now if we go less than 1.2, so let's go to 1 volt. Well, that means it should just output 1 volt. So 0.9, about. Something might be blocking some. Let me check this again real quick. Turn it off and then let me push these in, make sure that everything is getting. Let me check again. So yeah, 0.9. Okay. So yeah, that's what's happening, and our equations match up with our practical to some degree. And yeah, so something else you might be interested in is what is the voltage across each diode? Let me put this back in the middle here. At 1 volt, the voltage across each diode will be 0.45 and what? 0.43. So 0.43, 0.43, you see how it's over, they're the exact same. What's the voltage across each diode though? So you have some very small leakage current you're seeing. 0.03, 0.03, but they're all the same. It's about 0. Very, very close to 0. This is going to be negative, but it should still be 0.03. It's going to be very, very small. That, and with those 4 being about 0.03, that's about 1.2, or I guess 0.12 volts, 120 millivolts, you'll see that, and that's because of the leakage current due to those diodes. But yeah, so that's basically what's happening. You're seeing that there's technically no current in ideal cases. There's no current going through here because these are open circuit, just like in our analysis, when it's less than that threshold voltage to turn them both on. But if it's greater than, that's one more thing we could go to. We could test if it's greater than. I'm going to go back to 5 volts. So we're outputting 0.001 amps. We'll test the voltage across this, about 0.6, but now the voltage across each resistor, it's going to be the same. It's about 1 volt. And so what you'll see is 1 volt plus 1 volt plus 1 volt plus 1 volt, that's 4 volts. That means this should be about, I guess, half a volt. I guess if it's 0.95 though, you should really take into account that, right? So 0.95 times 4, so 0.95 times 4 is 3.8. Then you have 5 minus 3.8, it's about 1.2. Which is, you know, we had 0.6 and 0.6, that adds up to 1.2. So that's what's happening. This is a very simple diode circuit where we would see on an exam. And this is a more practical way about seeing this. So hopefully this helped y'all maybe understand this a little bit better. And I'll be making more. All right, thank you.